Okay, so how did structure emerge from this uniform so-called primordial soup? So the current universe is lumpy. It's very lumpy. Stars are about as soupy as water, and they're spaced away from each other by, even within a galaxy, which is a relatively dense place, they're a million diameters apart from each other. Galaxies are less dense. They're spaced, though, still maybe 20 or 30 or 50 diameters apart, depends on the environment. Less than that if they're in a rich cluster, but still, there's a fair amount of empty space. Galaxies are pretty lumpy, pretty easy to identify. Even galaxy clusters, the rich ones like Virgo and Coma, pretty easy to identify. They're lumpy. They're not nearly as lumpy as galaxies, and galaxies aren't nearly as lumpy as stars. But then that's also telling you something, right? That was how we decided that the dark matter must be cold dark matter. That was what we arrived at the end of our last lecture. So the initial density fluctuations, though, is now what we're wondering. So, you think of a hot gas, it's extremely uniform. So far, we haven't come up with any reason here why the universe should be lumpy at all. I mean, if the universe is flying apart at speeds that are comparable to the speed of light, why did anything at all form? Why didn't the individual atoms just fly apart and no structure at all? So that's our next set of observational clues. We want to know, how can the structure of the universe tell us what is the nature of the matter that is really being the gravity that is pulling stuff together and letting us see what we see. And so now we get to what we call topology, the geometric form of the matter concentrations in the universe. There's lots of possibilities. It could have been a meatball topology. That would be one where the density is concentrated into spherical or roughly spherical lumps surrounded by empty space on all sides and then another lump somewhere else. That's not the only possibility. That may be the easiest one to come to mind, but that's not the only other possibility. You could have the opposite of that. The Swiss cheese analogy, where the roundish things were actually the vacuums, and then the matter was where the cheese was. So then that would look a lot more complicated to try and draw. And then something that's sort of in between, a filamentary structure. So what does the universe really look like? Well, galaxies are tracers of the matter. They're tracers even of the dark matter. We already saw how the dark matter was concentrated around galaxies, that the density of dark matter is revealed by Vera Rubin's data, and all data since, that falls off as roughly 1 over r squared. The dark matter is densest right where the ordinary matter is, in the central bulge of our galaxy, and it's true for other galaxies as well. Okay, but the dark matter is not as concentrated as the light matter. But still, the light matter, the stars here, are like beacons shining within larger scale structures that tell us where the major matter that dominates the universe, the dark matter, actually is. So what do we see here? Well, we see what's called the Great Wall. This is towards the northern cap of the visible sky and looking towards our Milky Way. So that's the Great Wall. And there's the Great Wall of the South. And then there's kind of another wall there, and there's a bit of a wall there, and there's some filaments there. There's definitely filaments, but now I don't want you to get confused with another direction. Here's another filament. And that is this direction. Now, that's us, okay? We're there. And this direction here, why don't we see any galaxies here? That's probably the first thing you're wondering. Well, they deliberately took those out. This is actually an old, classic survey, a really important survey that first gave us great cosmological clues, done by Harvard University, Geller and Huckra were the initiators of the study. And this region here is so close to the plane of our own Milky Way galaxy, this angle here, that they said, you know, trying to judge brightnesses of galaxies and making sure we get them all is too hard. There's too much dust. It's too lumpy. It's too hard. You know what? We've got enough statistics. We're just going to throw this data away. So all the galaxies that were in here, we just threw them away, counting on that all these galaxies in these other directions, like cones, like those funny cones, you know, that dogs wear. This is sort of like what you're doing. You're looking sideways out of a cone. Think of a circular edge to the cone. It's up here and down here. And now we're going to project that cone onto the sky, and we're going to just take a slice out of it. So this is, in fact, the name's often given to the papers published here, a slice of the universe. And we're looking at the galaxies in that slice. And you can begin to see filaments. That's the point. Filaments. The universe is filamentary. Now, here's a deeper survey using infrared to help us, and going out much further. And now the filaments are more obvious. Actually, you know what? I want to go back for a moment. These vertical things here that are aiming right towards us, I never finished that thought, did I? This is the so-called fingers of God effect. God is pointing his evil hand, his fingers at us. You are sinful and evil, or whatever he's saying. Actually, these are not fingers of God. It's just a colorful language. What these are is the Doppler effect of the motion of galaxies inside dense, rich clusters. That's the Virgo cluster I just circled. And look at it. Some of it actually goes beyond us. If you just literally interpret the velocity, throw it into the Hubble formula, and infer what the distance is, you're going to get the wrong answer. Because there's a lot of that velocity that's not due to the expansion of the universe. It's instead due to the motion of clusters inside of galaxies, galaxy clusters. So you have to be careful. You have to be really careful. And if you're really careful, then you can find that these clusters actually have velocity. And this velocity is internal, and it shows itself as the fingers of God. So it's one reason why the Hubble formula is not super accurate when it comes to trying to get distances, especially nearby. Anyway, when you have a big survey like this, then the fingers of God effect is smaller, and it's a little more reliable as a distance indicator, at least if you're not worried about small-scale motions. The point is that the galaxies are knots within dark matter. The dark matter is arranged in a filamentary way. And in fact, that's exactly what we would expect. We would expect that the lumps in the universe created by dark matter, we'll come to a reason why later, but imagine that those lumps are just like amorphous lumps, kind of like elliptical galaxies. We talked about how they're triaxial. They're random collisions and random impact directions, and so you'd expect that all three dimensions would be different. Now imagine that in a context of an expansion. So what you would have is one particular direction would be, doesn't have to be along an X, Y, or Z direction, it can be any direction, but there would be some direction along which the galaxies would experience the maximum density contrast. They would be sort of lumpiest. You know, there'd be a real sharp direction. Okay, there's a lot of stuff here, and there's not so much stuff going away from it. And that's the direction from which the galaxies would get the clearest command from gravity to collapse along this direction. So you'd expect stuff to collapse into pancakes first. So take an amorphous lump. It's got three unequal dimensions to it. It's defined its principal axes along its directions, where the matter seems to be oriented. And along one dimension is going to be the flattest, and that dimension is going to be the dimension that it collapses the first. So what we say is that lumps in the universe collapse along to make pancakes, and then the pancakes collapse to make filaments, and then the filaments drain to the middle and make lumps, zero-dimensional things. So things go from being sort of three-dimensional to being sort of two-dimensional to being sort of one-dimensional, filaments, to being zero-dimensional, galaxy clusters. Now, the speed with which that happens is going to be faster for the lumpiest things and slower for bigger things that are less lumpy. And so what you'd expect that when you just take a snapshot of the universe at this moment in time, like we're doing now, 13.72 billion years after the beginning, that you're going to see lumps that are in all three phases of that evolution. And that's exactly what we see. So we see a mixture of filaments, sheets, and lumps. And that characterizes the large-scale topology of the universe. And that's exactly what you'd expect if the universe was dominated by cold, dark matter. All right, it's now 10:30. It's time for me to say goodbye. I'm going to end our meeting right now because it's time for you to start your quiz. Your quiz is